Now we enter multilinear algebra. Today we define multilinear functions, then the symmetric and alternating versions, and finally revisit two examples you have already seen: bilinear forms and the determinant. So yes, old friends are back for more unpaid labor. A linear function has one input. A multilinear function has several inputs, but it is still linear in each input separately. Freeze all the other slots, and the remaining slot should behave like an ordinary linear map, a surprisingly sensible generalization, which is honestly suspicious. Formally, a function t from v1 cross v2 up to vm into w is multilinear if it is additive and homogeneous in each slot. That means if you change only the I input, then t behaves linearly in that input. And of course you must require this for every I, because mathematics never stops at the easier option. Some quick examples. The dot product on a real vector space is bilinear. Matrix multiplication is also bilinear in its two matrix inputs. On the other hand, the function x squared times y is not bilinear, because in the first input it is quadratic, not linear. Sadly, not every formula earns admission. Now suppose all inputs lie in the same vector space. A multilinear function t from v to the m into w is called symmetric if reordering the inputs never changes the value. For example, the rearranging sigma equals open parenthesis 2, 1, 3 close parenthesis swaps the first two inputs and keeps the third fixed. If t stays the same under every such rearranging, then t is symmetric. A multilinear function is alternating if it becomes zero whenever two inputs are equal. An equivalent description is that swapping two neighboring inputs changes the sign. So after an even number of swaps the sign stays the same, and after an odd number of swaps the sign flips. Symmetric functions say, sure, move things around. Alternating functions say, fine, but there will be consequences. Here is the quick reason. If two neighboring inputs are equal, then swapping them changes nothing in the input, but an alternating function still multiplies the value by -1. So the value must equal its own negative. Hence it must be zero. Efficient and mildly cruel. The determinant is the most famous alternating multilinear function. It is multilinear in the columns of a matrix, and swapping two columns changes the sign. Therefore it is alternating. In particular, if two columns are equal, the determinant is zero. So all that earlier determinant work was secretly training for today. How considerate. A bilinear form is just a multilinear function with two inputs. It is symmetric if b of v, w equals b of w, v. It is alternating if b of v, v equals 0 for every v over a field whose characteristic is not 2. That is equivalent to saying b of w, v equals minus b of v, w. So bilinear forms are the first non-trivial place where these general definitions show up. So that is the basic landscape. Multilinear means linear in each slot separately. Symmetric means reordering inputs does not change the value. Alternating means swaps flip the sign. So repeated inputs kill the value. And your two main examples for now are bilinear forms and the determinant. Nice clean definitions. Which means later we will probably use them to build something much less clean.